Hi there everyone, and welcome back to another lesson of our Physics O-Level series. Today's chapter is Forces and Pressure. This is our third chapter. In this chapter, we're going to be learning about moments of force, equilibrium, center of mass, extension of springs, and many other different topics related to pressure and turning effects. So let's get into this right away, starting with moment of a force. So here we are on moment of a force. So as you can see, we have a heavy door here. And to open this heavy door, we must make the turning effect of our force as big as possible. So how should we push? First of all, we're going to look for the pivot. The pivot is the fixed point about which the door will turn, which is the hinge. As you can see, these are the hinges. So we're going to push with as big a force as possible and as far as possible from the pivot at the other edge of the door. That's why the door's handle is also fitted here. So to have a big turning effect, the person must push hard at right angles to the door. Pushing at a different angle gives a smaller turning effect. So the quantity that tells us the turning effect of a force about a pivot is its moment. And the moment of a force is bigger if the force is bigger. First point. So the quantity that tells us the turning effect of a force about a pivot is its moment. So what this basically is trying to say is that the force we applied on this door was a force that led to a turning effect. So the quantity of the turning effect of this force that we applied on the door is its moment. In simple words, we call this kind of force, this turning effect force, a moment. So the moment of a force is bigger if the force is big. So basically, the moment of a force is directly proportional with the force acting. If the force with which I am pushing the door is big, then the turning effect is also going to be big. If I push with less force, then the turning effect would also become less. So, moment of a force is bigger if the force is bigger. Second is that the moment of a force is bigger if it acts further from the pivot. This is the fixed point about which the door turns. This is called a pivot. The fixed point about which any object turns is a pivot. So, the moment of a force is bigger if the force that is acting on the door is further from the pivot. That is why we have a door's handle over here, because then it is easier to push it. If we push the door from at this point, then it will become hard. And the third point is that the moment of a force is greatest if it acts at 90 degrees to the object it acts on. So these were the 3 points that make the moment of a force bigger. First point is that the moment of a force is bigger if the force is bigger. Second, the moment of a force is bigger if it acts further from the pivot. And third, the moment of a force is greatest if it acts at 90 degrees to the object it acts on. And the quantity that tells us the turning effect of a force about a pivot is its moment. This is the definition of moment. Let's look at some examples. Here we are basically making use of turning effects, such as we use a crowbar to lift a heavy slab, lifting a load in a wheelbarrow. And the third is using a long spanner to loosen or tighten a nut. These are some examples of turning effects that we use in our daily life. Now let's look at equilibrium. So when a beam is balanced, we say that it is in equilibrium. If an object is in equilibrium, the forces on it must be balanced, which means there should be no resultant force. And the second point is that turning effects of the forces on it must also be balanced, which means no resultant turning effect. So as you can see, in this beam, there are 2 loads at this point and only 1 load at this point. So you can see that this is an example from which we can understand that when we apply a force away from the pivot, then we need a much less force. But when we apply a force closer to the pivot, we need a bigger force to make the bar something like this. As you can see, we need two loads to make this beam straight. But at this point, we need only one load. So the force is less on this side of the beam because it is further away from the pivot. These two loads are much more and they are closer to the pivot. So we have to apply more force on this side of the pivot to turn the beam and less force on this side of the pivot to turn the beam. So to make this beam balanced, we put two loads over here and only one load over here. Because if we put only one load over here and one load over here, the beam is going to lean at this side. And if we place only two loads over here and no load over here at all, the beam would go and lean over here and this side. We can also make this beam balanced by placing only one load over here at this point or over here maybe. So then it might get balanced because only one load over here would make it balanced. So this is the example of equilibrium, that the forces on this beam are balanced and there are no turning effects on this beam as well. There is neither any resultant force nor any resultant turning effect on this beam. So if a resultant force acts on an object, it will start to move off in the direction of the resultant force. We have understood this in the previous chapter as well, that when there is a resultant force on an object, it accelerates in that direction. But if there is a resultant turning effect, then the object will start to move. This is exactly what happens when we pick up the beam from this side. So when we pick it up, there is a resultant turning effect in this direction because there is much more force at this part compared to this part. So the beam starts to rotate like this. So this is the turning effect. Now let's look at how we can calculate moments. So moments are described as clockwise or anti-clockwise, depending on their direction. So the moment of a force is also called a torque. We can call it either a moment or a torque. It means the same thing. And this torque can be calculated using this equation. The equation is that moment of a force about a point is equal to the force into the perpendicular distance from the point. So the moment of a force about this pivot is equal to the force multiplied by the perpendicular distance from this pivot. Okay, let's see how we can use this equation in this example. So here we have a question. The weight on the right, which is this one, is tending to turn this beam clockwise. So the weight on the right has a clockwise moment and the two weights on this side have anti-clockwise moment. So first we're going to use this equation, moment of force about a point is equal to force into perpendicular distance from the point equation for this block over here. So for the clockwise moment first. The clockwise moment is equal to 500, which is the force of this block, multiplied by 2, which is the distance of the block from this pivot, which is 2 meters. So 500 multiplied by 2 meters and we get the clockwise moment, which is 1000 Newton meters. Now we're going to measure the anti-clockwise moment, which is, because we have two loads over here, we're going to measure each of them separately. First, let's look at the 400 Newton. The 400 Newton would be multiplied by 1 because this 1 meter is the distance it is from the pivot. But 300 Newton block is going to be multiplied by 2 meters because this is the distance it is away from the pivot. We're not going to see the distance between two forces. We're going to see the distance between a force from the pivot. So the distance of this force from the pivot is 2 meters, as it can be seen. So we're going to multiply 300 by 2 and 400 by 1, and then we're going to plus both of them, and what we get is 1000 Newton meter. So the clockwise moment is also 1000 meter and the anti-clockwise moment is also 1000 meter. So they are equal, which means that there is no resultant force and no resultant turning effect. So that is why this beam is in equilibrium. So this is how we use this equation to find out the answer of this question. Now let's do another question. It's good practice, and the more we use this equation in different kinds of questions, the better we get at using it and understanding it. The beam is 2 meters long and has a weight of 20 Newton. It is pivoted as shown, so the pivot of this beam is at this point. A force of 10 Newton acts downwards at one end, which is this one. What force F must be applied downwards at the other end, which is this one, to balance the beam? So as you can see, we have two forces over here. One is the force of 10 Newton acting at this point. The other is a force of 20 Newton acting at this point. Now, what the question is asking us to do is to find the force F. So when we find this force F, we can understand how this beam is balanced. So here we have the steps to do this question. The first step is to identify the clockwise and anti-clockwise forces. So two forces act clockwise, 20 Newton at a distance of 0.5 meter and 10 Newton at a distance of 1.5 meter. So we're not going to check this distance from force to force. No, we're going to check the distance from force to pivot, not force to force. This is 1 meter, but measure the distance of this force from the pivot, we get 1.5 meter. 1 plus 0.5 and 1.5 meter. So one force acts anti-clockwise, which is the force at 0.5 meter here. And we have to find this force. So since the beam is in equilibrium, we can write that total clockwise moment is equal to total anti-clockwise moment. So now we're going to substitute in the values and solve. The total clockwise moment is 20 Newton multiplied by 0.5 meter. So we're multiplying the force by its distance. And plus 10 Newton multiplied by 1.5 meter. So when we plus these two forces, we get, so what happens? So this is the clockwise moment. And the anti-clockwise moment is F into 0.5 meter, but the force of F, we need to find it out right now. So this is anti-clockwise moment and this is clockwise moment. This is how we put them here. So this is the clockwise moment, which basically 20 multiplied by 0.5 and we get 10, and 10 multiplied by 1.5 meter is 15 Newton meter. So we get these two on the clockwise moment side and F into 0.5 meter on this anti-clockwise moment side. So these are both equal. Both of them are equal. When we plus these two values, which are basically these two forces, we get 25 Newton meter. So the clockwise moment is equal to 25 Newton meter and the anti-clockwise moment is equal to F into 0.5 meter. So to find the value of F, we are going to divide 25 Newton meter by the distance of F. So the distance of F from the pivot is 0.5 meter and 25 Newton meter is the clockwise moment. So we're going to divide this clockwise moment by this distance, and what we get is 15 newtons. So a force of 50 Newton is needed at this end to balance the beam. You might have been able to work this out in your head as well by looking at this diagram. So the 20 Newton weight requires 20 Newton to balance it, and the 10 Newton at 1.5 meter needs 30 Newton at 0.5 meter to balance it. So the total force needed is 50 Newton. So 30 plus 20 and we get 50. So this force had to balance this force as well as this force. So that is why we get 50 newtons at this point. So a force of 50 Newton is needed. This is how we write the answer. We're going to write the answer always in a sentence. A force of 50 Newton is needed. Okay, despite the three forces on this seesaw, there's also the weight of the seesaw itself, which also acts downwards through its midpoint. But if these were the only forces acting, like 200 Newton, 500 Newton, 400 Newton, 300 Newton, they would make the seesaw accelerate downwards. So there is another upward contact force. This is the contact force, where the seesaw sits on the pivot, preventing this from happening. So this is the contact force. This pivot basically sits on the ground, and the ground gives another upward contact force which is equal to all of these forces, 1400 Newton. This basically cancels all of these forces, and that is why the seesaw doesn't accelerate downwards. Because the seesaw is in equilibrium, the contact force must balance the 4 downward forces. So we can calculate 500 plus 200 plus 400 plus 300, and we get 1400 Newton. And this force has no turning effect because it acts through the pivot. So its distance from the pivot is 0, so its moment is also 0. That is why it doesn't have any turning effect. Okay, now we have satisfied the 2 conditions that must be met if an object is to be in equilibrium. The first condition is that there must be no resultant force acting on it. Of course, if there is a resultant force on an object, the object will accelerate in that direction of the resultant force. Basically, motion will come in and the object will not be in equilibrium. And the second condition is that total clockwise moment is equal to total anti-clockwise moment. This also means the same thing, but it just says that there should be no resultant turning effect. No turning effect. That the total clockwise moment should be equal to the total anti-clockwise moment, so this would make there 0 resultant turning effect. Okay, so these are the 2 conditions that must be met if an object is to be in equilibrium. We can use these 2 rules to solve problems concerning the forces acting on objects in equilibrium. Okay, now that we've understood equilibrium and moments of force and the equation we used for moment, which is moment of a force about a point is equal to force multiplied by perpendicular distance from the point, and we get the moment of a force about the point. So this is the force equation, and another equation, and the equation for equilibrium is total clockwise moment is equal to total anti-clockwise moment. So now that we've understood and cleared all of these things out, we can move ahead on to understanding center of mass. Let me tell you that these are the basically 2 rules which you can also test by these following examples I'm going to be telling you. For example, take a long light wooden beam, for example a half meter rule is suitable, and balance this beam at its midpoint. Then you need not to worry about the weight of the beam, because when it is balanced there is no forces acting on the beam. So we can use sharpener to balance the ruler on, and then we're going to place 2 or more weights at different points along the beam, along the ruler, and position the weights so that the beam remains balanced. For example, place 2 or more erasers at either end of the beam. Of course, one eraser might be heavy and the other might be light, so we're going to just put the weights at different points along the beam and position them at their perfect places so that the beam stays in balance. For each weight, calculate its moment. Note whether it's clockwise or anti-clockwise. Each weight, we're going to calculate its moment, and we're going to add up all the clockwise moments and the anti-clockwise moments, and the 2 totals should be equal if the beam is balanced. You will need to repeat this several times, so a single set of measurements will not be enough to test the principle of moments properly. This was just an investigation you can do to test the principle of moments. Anyways, now let's move ahead on to understanding center of mass. So people are tall and thin, like a pencil standing on end. But unlike a pencil, we do not topple over when touched by the slightest push. We are able to remain upright and to walk because we make continual adjustments to the positions of our limbs and body. So we need a considerable amount of brain power to control our muscles for this. And the advantage is that with our eyes about a meter higher than if we were on all fours, like cats and dogs, we can see much more of the world. Circus artists such as tightrope walkers have developed the skill of remaining upright to a high degree, and they use items such as poles and parasols to help them maintain their balance. So the idea of moments can help us to understand why some objects are stable while others are more likely to topple over. So, a tall and slim cylinder is easily knocked over because it is unstable. So here we have how this cylinder topples over. This is the first stage, stage A. When the cylinder is upright, its weight acts downwards and the contact force of the table acts upwards. So the two forces are in line, as you can see. The weight of the cylinder is represented by this downward arrow and the contact force is represented by this upward arrow. And as you can see, both the forces are in line. That is the reason why the cylinder is upright. Now over here, when the cylinder is tilted slightly to the right, the forces are no longer in line. So there is a pivot at the point where the base of the cylinder is in contact with the table, which is this point. This is the contact force, as you can see. And this basically becomes the pivot. So the line of the cylinder's weight is to the left of this pivot. So it has an anti-clockwise moment which tends to tip the cylinder back to its upright position. So because it is in this direction, this one, then it comes back to its position. But as you can see in this example, the cylinder is tipped further and its weight acts to the right of the pivot and has a clockwise moment which makes the cylinder tip right over. So because the weight now has a clockwise moment, it will just fall off, it will topple over. But over here, the weight had an anti-clockwise moment, so it came back to its upright position. Okay, now let's look at the center of mass. Now, if you see a champagne glass with some juice in it, then the weight of the glass will be represented by an arrow starting at a point inside the liquid in the bowl of the glass. Why is this? The reason is that the glass behaves as if all of its mass were concentrated at that point. This is known as the center of mass. So the glass is top heavy because the center of mass is high up. So there is more mass at the top of the glass than at the bottom. So the force of gravity acts on the mass of the glass, and each bit of the glass is pulled by the Earth's gravity. Okay, however, rather than drawing a lot of arrows, one for each bit of the glass, it is simpler to draw a single arrow acting through the center of mass, just like we are showing the arrow of this cylinder. Because we can think of the weight of the glass acting at this point, it is sometimes known as the center of gravity as well. So here we have some objects and their center of masses. So we have a conical shape. This has a center of mass right over here. A sphere, something like this, has a center of mass here. We have a pyramid as well. So these are some different interesting shapes and their center of masses. A person is fairly symmetrical, so their center of mass must lie somewhere on the axis of the symmetry. This is because half of their mass is on one side of the axis and half on the other. So the center of mass is in the middle of the body, roughly level with the navel. A ball is much more symmetrical, as you can see, and its center of mass is at its center. For an object to be stable, it should have a low center of mass and a wide base. For example, this pyramid here. The Egyptian pyramids are among the wonders of the world. It has been suggested that if they have been built the other way up, they would have been even greater wonders. But of course, they would not have been stable that way because they wouldn't have a bigger base. Now let's look at how we can find the center of mass of an object. So, balancing is the clue to finding an object's center of mass. A meter rule balances at its midpoint, so that is where its center of mass must lie. So the procedure for finding the center of mass of a more irregular shaped object is as follows. Say, for example, we have this piece of card over here. It's very irregular in shape, and we can't understand where the center of mass of this object would lie. This object is a piece of card, and this is described as a plain lamina. This card is suspended from a pin, as you can see. So if it is free to move, it hangs with its center of mass well below. So if it is free to move, it hangs with its center of mass below the point of suspension. So this is because its weight pulls it round until the weight and the contact force at the pin are lined up. Then there is no moment about the pin. So then a plumb line is used to mark a vertical line below the pin. The center of mass must lie on this line, as you can see. This procedure is repeated for 2 more pinholes, as you can see. We are hanging it now from a different point. 2 lines might be enough, but it's advisable to use at least 3 points to show up any inaccuracies. Now there are 3 lines on this card, and the center of mass must lie on all of them. That is, at the point where they intersect. And so as you can see, this is the point of intersection. So this is where the center of mass of this card is. So this is a method to find the center of mass of a regular shaped object. Now that we've understood center of mass and how we find the center of mass, we can move ahead on to understanding elastic and plastic. If you bend a ruler slightly and release it, it springs back to its original shape. Materials like this are elastic. However, they stop being elastic if they are bent or stretched too far. So they either break or become permanently deformed. But if you stretch or bend plasticine, it keeps its new shape. So materials that behave like this are plastic. Okay, so this was just a small information about elastic and plastic, the difference between both of them. Now, let's investigate how objects deform. So, to investigate how objects deform, it is simplest to start with a spring. Springs are designed to stretch a long way when a small force is applied, so it is easy to measure how their length changes. So here we have an experiment on a steel spring. In this experiment, a steel spring is stretched by hanging muscles from one end. As you can see, these are the muscles. The force applied to the spring is called the load. As G is 10 Newton per kg, the load is 1 Newton for every 100 grams of mass hung from this spring. So, as the load increases, the spring stretches more and more. Its extension is the difference between its stretched and unstretched lengths. So this is the pattern observed as the load is increased in regular steps. The length of the spring also increases in regular steps. At this stage, the spring will return to its original length if the load is removed. This is the original length. However, if the load is increased too far, like over here, the spring becomes permanently stretched and will not return to its original length. So, as you can see, this spring has stretched far too much. So, it has crossed this line. This was the line which showed that the spring's length was increasing in regular steps, but over here it increased too much. So this spring has been inelastically deformed and it will not return to its original length again. So this reading can also be plotted as a graph, like here. Up to point X, the graph line has these features. The line is straight and it passes through the origin, as you can see. If the load is doubled, the extension is also doubled, and so on. Extension divided by load always has the same value, which is 10 mm per Newton. And every 1 Newton increase in load produces the same extra extension, which is 10 mm. So, mathematically, these can be summed up. So up to point X, the extension is proportional to the load. So X is the limit of proportionality. And up to point E, the spring behaves elastically and returns to its original length when the load is removed. So E is its elastic limit. Beyond E, the spring is left permanently stretched. So there's a difference. Proportionality limit basically tells us that the extension of the spring, it doesn't come back to its original length. If we go up to this point, like we cross the proportionality limit, then what will happen is that the spring would behave elastically. So the spring will behave elastically and will return to its length, but it will not be its original length. It would be a different length, which would be basically more than the original length. But if the spring crosses the elastic limit, it will not come back, which means that if it's crossed the elastic limit, the spring is left permanently stretched and it will not return to any length. The bounce effect of the spring would be gone completely. It will not be elastic anymore, in other words. So this is the difference between proportionality limit and elastic limit. Proportionality limit basically tells us that the spring will come back because it hasn't crossed its elastic limit yet. So it will bounce back to its original length, but it will not exactly be its original length. It will be more than that because it has crossed its proportionality limit. So the proportion would not be correct. But if it has crossed its elastic limit as well, then the spring would not return to any length. It will just stay there forever. It is basically permanently stretched. So the spring is left permanently stretched. So as the force stretching the spring increases, it gets longer. So it is important to consider the increase in the length of the spring. And this quantity is known as extension. Dividing the load by the extension always gives the same value. And this value is called the spring constant. So as you saw in this graph, up to point X on this graph, dividing the load by the extension always gives the same value. This is the equation we use to measure the load of the spring. Load is equal to spring constant into extension. By spring constant we mean the original length of the spring. And in symbols we have this: F is equal to K into X. K is equal to spring constant, X is the extension, and F is the load. So knowing K, we can also use this equation to calculate the extension produced by any load up to the limit of proportionality. For example, if a spring constant is 0.1 Newton millimeter and the load on it is 2.5 newtons, then what will be its extension? To find the extension, we would need to rearrange this equation. And whenever I talk about rearranging the equation, I always remind you of the triangle we use. So this is an equation. Now remember the triangle. The triangle has two values at the bottom which are multiplying and one value at the top which divides with both the values. There's only one pair that is going to multiply together to find something, and this is the pair of that. So of course load would not multiply by spring constant to find extension. Neither would extension be multiplied by load. They will always be divided. There is only one pair which is going to be multiplying, which is, as you can see, it is spring constant into extension. So we're going to keep these two values below and make a line above and place the load above. So what we get is that if we have to find the extension, we would divide the load with spring constant, and if we have to find the spring constant, we would divide the load by the extension. Very simple. We can even make it in our head. So to find the extension, we would divide the load, which is 2.5 Newton, with the spring constant, which is 0.1 Newton per millimeter. Let's do this right now. So here we have 2.5 divided by 0.1 and we get 25. So 25 millimeter is the extension of the spring. So this is how we use this equation to find extension, spring constant, or the load of it. Now we are going to look at Hooke's law. So in the 1660s, Robert Hooke investigated how springs and wires stretched when loads were applied. So he found that for many materials, the extension and load were in proportion, provided the elastic limit was not exceeded. So a material obeys Hooke's law if beneath its elastic limit, the extension is proportional to the load. So in this graph, as you can see, the spring obeyed Hooke's law till this point X. This was the proportionality limit. After this, the spring lost its proportionality and it was now deformed. But before this point, it was completely straight. So if we had divided extension by the load, it would always have the same value. So this basically obeys Hooke's law, but after the proportionality limit, it doesn't obey Hooke's law. So Hooke's law states material obeys Hooke's law if beneath its elastic limit, the extension is proportional to the load. Steel wires do not stretch as much as steel springs, but they do obey Hooke's law. Glass and wood also obey the law, but rubber does not. So now that we've understood Hooke's law, let's move ahead on to doing some questions over here. So the question is saying that a spring of original length 10 cm stretches to 12 cm when a force of 40 Newton is applied to it. So what is the extension of the spring when a force of 26 Newton is applied? Okay, so the spring has an original length 10 cm and it stretches to 12 cm when a force of 40 Newton is applied. And now it's asking us if a force of 26 Newton is applied, what would be the extension of the spring? So the first method to answering this question is by using the stiffness constant. So first we're going to calculate the extension and the value of K. By K we mean the spring constant. So force is equal to 40 Newton and the extension would be 12 minus 10 and we get 2 cm. So here we have the force and the extension. To find the spring constant, we're going to use both the values. So what we're going to do is divide force by the extension and basically you divide 40 by 2 and we get 20 Newton per centimeter. So this is the stiffness constant. So this is basically the spring constant. Now we use this value of K to find the new extension and the new length. So now we know the stiffness constant and we know the new force, so 26 Newton. So to find the extension, we're going to divide this force by the spring constant, 26 by 20, and what we get is 1.3 centimeter. So 1.3 centimeter is the extension. So we have given the extension, so the new length would be the original length plus the extension. So the original length is 10 and we add the extension 1.3 centimeter and we get 11.3 centimeter. So the new length is 11.3 centimeter. Now the second method to answering this question is by using direct proportionality. So first we find the extension at one value of force. Extension is equal to 12 minus 10 and we get 2 centimeter when the force is 40 Newton. Now we use direct proportionality to find the extension for a new force. So the new force is 26 Newton. The extension would be equal to 26 Newton divided by 40. Basically, the new force dividing by the previous force and then we multiply it by 2, which is the extension. And we get 1.2 centimeter. So again, we just add this extension in the original length and we get the answer. So this is the second method by using the direct proportionality to find the answer. So this was just a small question and to find the answer in different ways and play with this equation. Now that we've understood the extension of springs, we're going to move on to understanding pressure. Understanding pressure. Surgeons use very sharp knives and needles when performing operations on patients, which cuts through skin and flesh with the minimum of force. So this ensures that the minimum of damage is done when a patient is opened up and sewn. So knives and needles have sharp blades and tips in order to concentrate the force that is being applied onto a small area. This means that the pressure that is being applied is as large as possible. So pressure tells us how concentrated a force is. If a force is concentrated on a small area, its pressure is high. So here's what I'm trying to say. This surface, as you can see, is bigger than the object. So the pressure is not that much compared to this one. This block has a higher pressure because it has a smaller area and the object is bigger. So the object is the same, but it depends on the area. Here we have a bigger area, so the pressure is less. And here we have a small area, so the pressure is high. Knives have sharp blades to give a high pressure. Ice skates also have blades. The part that is in contact with the ice, this is the blade. This is narrow so that the skater's weight is concentrated on a small area. The effect of this high pressure is to melt the ice just below the blade. So this gives a thin film of water, which provides the lubrication for the skate as it skims over the ice. So as the skate moves on, the water refreezes. But on very cold days, the pressure may not be enough to melt the ice, and skating is impossible. So another example of high pressure and low pressure is if you are unlucky enough to find yourself standing on thin ice, it is advisable to lie down on it to spread out your weight. So this reduces the pressure and the ice is less likely to break, because the area would be bigger and it would be less, and the pressure would be less. When we are standing, all the weight is concentrated at a smaller area, such as this pin. It's a very small area and the pressure is obviously high. So onto a smaller area, the minimum of force gives a higher pressure. That is why knives and needles have sharp blades and tips, so the force is more concentrated. The same principle is used elsewhere, such as, for example, crawling boards are often used to climb over glass roofs. These spread out the weight of anyone needing to climb on a roof. Some vehicles are fitted with very wide tires, another example, so that they exert less pressure on soft grounds. For like big vehicles, so that is why bigger cars have big tires as well, to reduce the pressure on soft ground. Camels also have big flat feet for the same reason, to reduce the pressure on the sand so that they are less likely to sink in and become bogged down. If force is measured in newtons and area in square meters, pressure is measured in newtons per square meters, Newton/meter square. So in the SI system of units, this is given the name Pascal. So this is the equation we use to find pressure. Pressure is equal to force divided by area. In symbols, we write it as P is equal to capital F upon capital A. Okay, let's look at a problem of pressure over here. The wind pressure on a wall is 100 pascals. So if the wall has an area of 6 meters square, what is the force on it? So to solve this, you need to rearrange the pressure equation. So make it force is equal to pressure into area, and we just get the answer simply because we multiply the pressure with the area given, and what we get is 600 Newton. So the force on the wall is 600 Newton. It's very simple, isn't it? Here we have another example. So a concrete block has a mass of 2600 kg. The block measures 0.5 meters into 2 meters into 1 meter. What is the maximum pressure it can exert when resting on the ground? So to measure volume, we basically measure the sides of the blocks, the width, the height and the length. So we don't know which is which over here, but we can still assume that the smallest area is 0.5 meters compared to the rest of them. So what is the maximum pressure it can exert when resting on the ground? If it is resting on the ground with this side, then it will be the maximum pressure. Anyways, let's look at it now. As the downward force is 10 Newton per kg, the 2600 kg block has a weight of 26,000 Newton. What we just did is multiplied the mass with the gravitational field, gravitational force to find the weight. So the force on the ground of the block is 26,000 Newton. So to exert maximum pressure, the block must be resting on the side with the smallest area. This is the side measuring 1 meters. So its area is equal to 1 meter into 0.5 meter. So pressure is equal to force upon area. So we multiply the weight of the block with the area, which is 0.5 meter square, and what we get is 52,000 pascals. So the maximum pressure is 52,000 pascals or 52 kilopascals. You can also write it as that. So it's just a very simple way to use this equation. Now let's look at the pressure in liquids. Pressure in liquids is different from pressure in solids. So here are some points to remember about pressure in liquids. A liquid is held in its container by its weight, and this causes a pressure on the container and pressure on any object in the liquid. So here we have the properties which apply to any stationary liquid in an open container. Firstly, pressure in liquids acts in all directions. So basically, in a fluid such as water or air, pressure does not simply act downwards. It acts equally in all directions. This is because the molecules of the fluid move around in all directions, causing the pressure on every surface they collide with. So the liquid pushes on every surface in contact with it, no matter which way the surface is facing. Deep sea vessels have to withstand the crushing effect of sea water pushing in on it from all sides, not just downwards. That's why most submarines and marines are spherical in shape. Second point is that the pressure increases with depth. The deeper into a liquid you go, the greater the weight of the liquid above and the higher the pressure. Here we have another example over here. Over here, the pressure is less at this point. It increases at this point and it has the maximum pressure at this point, as you can see. Third point is that the pressure depends on the density of the liquid. The more dense the liquid, the higher the pressure at any particular depth. Fourth point is that pressure doesn't depend on the shape or width. The pressure at any particular depth is the same. So as you can see, we have different shapes of objects, but the pressure of the liquid at any point in these blocks would be the same in each one of them. If it's 2 pascals over here, then it would be same in everyone. It would be 2 pascals over here, and all of them would have the maximum pressure at this point. So pressure does not depend on the shape or width of an object, of a container. Now let's look at how we can calculate liquid pressure. So here we have a question. A container has a base area A, and this container is filled to a depth h with a liquid of density P. So to calculate the pressure on the base due to the liquid, you first need to know the weight of the liquid on it. So first we're going to find out the volume of liquid. How do we find the volume of liquid? We multiply the base area of the container with the depth of the container, which is AH, as you can see. Then we find the mass of liquid. So we multiply density with volume to find mass. So the equation now becomes PAH. AH is the volume of the liquid and P is the density. Then we have to also find the weight of the liquid. The weight of the liquid is equal to mass into G. So what happens is, because density is multiplying by volume, P into AH is equal to mass. So we have to add gravity in it as well, so that we can measure the weight of the liquid as well. So the force on the base is equal to PGAH. This is the equation we use to find the force on the base of a liquid. So this force is acting on an area A. So pressure is equal to force upon area is equal to PGAH upon A. So these A's get cancelled. So the area gets cancelled with the lower area, and the equation in the end is PGH, not PGAH. Now the equation has become PGH. Pressure is equal to PGH. So this was the equation. Now if anybody asks what the pressure of the liquid is, we multiply the density of the liquid with the gravity of the liquid. So we're going to multiply these 3 values and we get the pressure. Density into gravity into the depth of the liquid. That's it, and we get the pressure. So this is the equation we use to calculate the pressure in liquids. Density comes in, gravity comes in. So this is different from the equation we use to calculate the pressure on solid objects. Also, for a change in depth, the change in pressure would be equal to PGAH, PG delta H. Delta means change in. So change in depth is basically delta H. So change in pressure is delta P. So delta P is equal to Pg delta H. For example, if the density of water is 1000 kg per meter square, what is the pressure due to the water at the bottom of a swimming pool 2 meters deep? So what we're going to do is the liquid pressure equation. 1000 kilograms per meter square is the density, and we multiply it with the height of the liquid and multiply it by 10, which is the gravity, and we get the answer. To find the change in pressure, we use Pg delta H equation. Delta H means the change in depth. So what the depth was before and what it is now. Basically, we minus the previous depth with the initial depth and we find the change in depth. So P multiplied by G multiplied by delta H, and then we will find the delta P. So this was the equation of liquid pressure. Now let's look at pressure in atmosphere. So the atmosphere is a deep ocean of air which surrounds the earth. In some ways it is like a liquid because its pressure acts in all directions just like liquid, and its pressure becomes less as you rise up through it because there is less and less weight above. So these 2 points are very much like a liquid. But unlike a liquid, air can be compressed. This makes the atmosphere denser at lower levels. The atmosphere stretches hundreds of kilometers into space, yet the bulk of the air lies within about 10 kilometers of the Earth's surface. So here we have some examples of atmospheric pressure. So over here we're doing an experiment. Here we have a metal can, and this can is empty. There is no liquid in this can. This metal can is heated, and after heating the can, we put it into cold water. What happens is that as the metal can cools down, atmospheric pressure crushes the can. What happens is that basically when we heat the can and when we cool it, then the air gets removed. So inside the can there is nothing to resist the outside pressure, and the can is crushed by the atmospheric pressure. So another example is when we are drinking through straw. You expand your lungs to reduce the air pressure inside the straw. As a result, atmospheric pressure outside the straw pushes the liquid up the straw. It's very fun to understand such simple concepts. When we are drinking through a straw, we don't even know what physics is behind this straw. But now we do know. It is atmospheric pressure that basically pushes the liquids up the straw because the pressure inside the straw is less. Another example is the vacuum cleaner. So in the vacuum cleaner we have a fan. The fan of this vacuum cleaner lowers the air pressure just beyond the bag. So this is the dust bag. So the pressure is reduced in this bag. What happens is that the atmospheric pressure rushes in carrying dust and dirt with it because the pressure inside is less. So basically the atmospheric pressure then pressures it. And the bag acts as a filter, stopping the dust and dirt but not the air. So the atmospheric pressure brings in dust and dirt inside, but the bag just keeps the dust and dirt and the air goes out from this side. So the dust bag acts like a filter. So this is the physics of vacuum cleaner. So this was the vacuum cleaner and this was the pressure in atmosphere. Now we're going to look at the instruments we use to measure pressure. On number 1 we have the Mercury Barometer. So instruments that measure atmospheric pressure are called barometers. Remember, these instruments only measure the atmospheric pressure, not the liquid pressure. So this barometer contains liquid metal mercury. The atmospheric pressure has pushed the mercury up the tube because the space at the top of the tube has no air in it. It is a vacuum. So the mercury over here is compressed by the atmospheric pressure and the level goes up. So at sea level, atmospheric pressure will support a column of mercury 760 mm high on average. For convenience, scientists sometimes describe this as a pressure of 760 millimeters of mercury. However, it is easily converted into pascals and other units. The actual value of atmospheric pressure varies slightly depending on the weather. Rain clouds form in large areas of lower pressure, so a fall in the barometer readings may mean that rain is on the way. Atmospheric pressure also decreases with height above sea level. This idea is used in the altimeter as well, an instrument fitted in aircraft to measure altitude. So the barometer has a glass tube with mercury inside. This dish also has mercury. This is basically like an inverted glass tube. And we have a vacuum over here. So this length of the mercury inside this glass tube is measured in millimeters. So at sea level, the atmospheric pressure will support a column of mercury 760 millimeters high. In inches, it is 29.92. Standard atmospheric pressure. So the pressure that will support a column of mercury 760 millimeter high is known as standard atmospheric pressure, or 1 atmosphere, 1 atm. We can also call atmosphere atm. For example, at a depth h in a liquid of density p, the pressure is equal to pgh, where g is the gravitational force. We usually call it 10 Newton per kg, but right now we are using the more accurate measurement, which is 9.807 Newton per kg. So as the density of mercury is 13,590 kilograms per meter square, and the height of the column is 0.7600 millimeters, then 1 atm is equal to pgh. So we multiply the three values: the depth of the mercury, the density of the mercury, and the gravitational force. We're going to use the accurate one over here in this example. And what we get is 101,300 pascals. But in calculations for simplicity, we can assume that 1 atm is equal to 100,000 pascals. So this is how the standard atmospheric pressure comes from. We use the pGH equation here to find the pressure. So to find pressures through this mercury barometer, we have to use the pGH equation. What we do is multiply the height of this barometer with the density and the gravitational force to find the pressure. So this level of mercury might be less or more in different places. Standard atmospheric pressure at sea level, it supports a column of 760 millimeters high. So the standard atmospheric pressure, after all this calculation, we get 100,000 pascals. Okay, now that we've understood atmospheric pressure and the standard atmospheric pressure and the mercury barometer, we can move ahead onto another instrument which is called the manometer. In weather forecasting, the millibar, also known as MB, is often used as the pressure unit. 1 millibar is equal to 100 pascals. So standard atmospheric pressure is approximately 1000 millibars. So here we have the manometer. As you can see, it is a U-shaped tube. So a manometer measures pressure difference. It doesn't measure the pressure, it measures the pressure difference. So the height difference, as you can see over here, shows the extra pressure from this point to here. This is the difference of the height of the pressure. So this basically shows the extra pressure that the gas supply has in addition to the atmospheric pressure. This extra pressure is called the excess pressure. So to find the actual pressure of the gas supply, you add the atmospheric pressure to the excess pressure. So this was the manometer. It's a very simple tool, as you can see. It just measures the pressure difference. How do we measure the pressure difference? We see the height difference, which is this. This is basically the extra pressure. This shows the extra pressure that the gas supply has in addition to the atmospheric pressure. And this extra pressure is called the excess pressure. So to find the actual pressure of the gas supply, we add the atmospheric pressure to this excess pressure. Now let's move ahead on to understanding gas pressure and volume. When dealing with the fixed mass of gas, there are always three factors to consider: the pressure, the volume, and the temperature. A change in any one of these produces a change in at least one of the others. So often all three change at once. This happens, for example, when a balloon rises through the same atmosphere or gases expand in the cylinders of a car engine. So the link between the pressure and the volume can be found from this experiment. So in this experiment, the temperature is constant. So this gas is being studied. The gas being studied is a fixed mass of dry air. The air is trapped in a glass tube. Its volume is reduced in stages by pumping air in the reservoir so that the oil is pushed further up the tube. This is the air which is pumped in the reservoir, so this oil basically gets up and the volume decreases. So each time the volume is reduced, the pressure of the trapped air is measured on this gauge. So here we have the results. Let's read them out first. So when the volume was 1.3, the pressure was 60. When the volume decreased to 88 cm3, the pressure increased and became 70 kilopascals. Anyways, in the end, when the volume is 31 cm3, the pressure is 200 kilopascals. So these results basically show that the relationship between the pressure and volume is an inverse proportion. By inverse proportion, we mean that if volume increases, the pressure decreases, and if the pressure increases, the volume decreases. We can also show this using a graph here, that the pressure increases when the volume decreases. So volume decreased, the pressure increased. Decrease and it increased. So this is how it is shown using a graph. So what happens is that when we squash the air, basically when the volume is reduced, the air gets squashed. It warms up slightly. So before taking each reading, we have to wait a few moments for the air to return to its original temperature. So the gauge actually measures the pressure in the reservoir. But this is the same as in the tube because the oil transmits the pressure. So the results of this experiment have these features. Firstly, if the volume halves, the pressure doubles, and so on. This is basically the inverse proportion. Secondly, pressure multiplied by volume always has the same value. And number 3, if pressure is plotted against 1 divided by volume, the graph is a straight line through the origin. So the findings can be expressed as a law. Boyle's law. Here are the features that I just read, and here is what we're talking about here. Boyle's law. For a fixed mass of gas at a constant temperature, the pressure is inversely proportional to the volume. This is known as Boyle's law. So here is another way of writing Boyle's law. If the pressure is changed from P1 to P2, when the volume is changed from V1 to V2 at constant temperature, P1 into V1 is equal to P2 into V2. So I bet this is a much complicated way to express Boyle's law. But this is basically an equation that pressure 1 into volume 1 should be equal to pressure 2 into volume 2. Only then it will obey Boyle's law. If they are not equal, it will not obey Boyle's law. The kinetic theory explains Boyle's law like this. In a gas, the molecules are constantly striking and bouncing off the walls of the container. The force of these impacts causes the pressure. So if the volume is halved, there are twice as many molecules in each cubic meter. So every second there are twice as many impacts with each square meter of the container walls. So the pressure is doubled. Boyle's law, pressure increases when volume decreases. Here the pressure was less compared to this place. So this is Boyle's law. Pressure increases when volume decreases. A gas that exactly obeys Boyle's law is called an ideal gas. So real gases come close to this provided they have a low density, a temperature well above their liquefying point, and are not full of water vapor. So unless these conditions are met, the attractions between molecules affect their behavior. So an ideal gas has no attractions between its molecules. So this was the third chapter of our physics O-level lessons, forces and pressure. We just completed it successfully, and as you can see, in this chapter we understood the moments of forces, turning effects, we understood equilibrium when forces are balanced. We also learned the equation we used to find the moment of a force about a point, and we did questions related to it. Then we understood the center of mass, how we can find the center of mass. We understood the difference between elastic and plastic, and then we understood the extension of springs. We understood Hooke's law, the limit of proportionality, the elastic limit, the equation we used to find the extension of a spring, a question related to it, Hooke's law. We did a question related to the extension of springs, and we used two different methods to answer it. After this, we learned about pressure, the equation of pressure, did some pressure problems, of course, and then we understood about pressure in liquids. We understood how we can calculate liquid pressure, a tiny bit of example here, and then we understood the pressure in atmosphere. Examples of pressure, atmospheric pressure. And then we understood the Mercury Barometer and the standard atmospheric pressure. After this, we understood the manometer, what is the manometer and what it measures. And then we understood gas pressure and volume, how we link pressure and volume, the experiment we used to find the link between the pressure and volume. In simple words, we understood Boyle's law in this section. And then lastly, we understood how the kinetic theory explains Boyle's law. So this was all about this chapter, forces and pressure. The next chapter is going to be forces and energy. So this was all about today's video, and I will see you in the next chapter.